Hello AP Chem students and welcome to topic 7.12, the common ion effect. The learning objective for today is 7.12.a, identify the solubility of a salt and or the value of KSP for the salt based on the concentration of a common ion already present in solution. So the learning objective actually defines for us what a common ion is, but it's something that you need to think about when you're working with solubility equilibria. So in the previous section, in section 7.11, we were looking at dissolving salts in pure water. Sometimes we dissolve salts in a solution that already exists. So there's already something else dissolved in the water before you add a solid to it. When something is dissolved in the solution that is already, that is part of the solid you're adding, that's called a common ion. And that impacts the solubility. So the common ion effect is the decreased solubility that occurs when a starting solution already contains one of the ions that is present in the added solid. So it looks like this. So if this is just pure water and we try and dissolve calcium fluoride, you can see, of course, stoichiometrically, we have our correct ratio here. We dissolve 2 fluorides for every 1 calcium. And you can see that we have this situation. But if we add sodium fluoride, that means we're going to flood the solution with fluoride ions. You're going to see that a calcium fluoride precipitate will form. And essentially what we have done is shifted your equilibrium. So we've added one of the components of the products, and so that has shifted the equilibrium back towards the reactants, which is the solid. So it's an application of Le Chat. So when you're calculating concentrations for the KSP value, you use your Rice method, with the initial being before the dissolving occurs and the equilibrium is established after adding the solid. So we're going to look at an example which I hope, or which will make it make more sense. So we're going to be in practice 15. This is our last practice problem for unit 7. Calculate the solubility of solid CaF2 with a KSP value equal to 4.0 times 10 to the negative 11th in a 0.025 molar sodium fluoride solution. And if you want to try this on your own first, go ahead and pause the video now. Okay, so as we have been doing this entire unit, we're going to start with a Rice table, right? So here is your reaction. CaF2 dissociates into calcium 2 plus 2F minus. Remember that because we're working with ions here, we do not express F as a diatomic. That's only when F is found in its elemental form. This is not fluorine in its elemental form. This is fluoride. So it has a charge and this is different. Okay. So our initial is going to be, we have no calcium initially, so that's going to be 0, but we do have fluoride present. So this is one of the first times, or this is the first time with solubility that we've looked at having an initial that is not 0. And so this initial for fluoride is going to be 0.025. Now note that this is your initial concentration, so we don't take into account the coefficients at this point because this is how the solution exists before we add the CaF2 into it, okay? So initially, before the solid starts dissociating. When it does dissociate, we're gonna have plus X for Ca, plus 2X for F minus, and then 0 plus X is equal to X, 0.25 plus 2X is our equilibrium for our F minus. So our KSP expression is gonna be equal to the concentration of Ca2 plus, times the concentration of F minus squared. Again, that coefficient becomes a superscript in our KSP expression. We do not have a denominator because we do not include solids in our equilibrium expressions. And so now we need to think about the fact that solubility is equal to X. And so we're going to be solving for the value of X. Now we can simplify this calculation quite a lot by recognizing that the starting concentration of F minus is much, much greater than your KSP value, right? And when we solve for X, we do that by mathematically examining our KSP value. So because this is so much larger than your KSP, we can ignore X according to the 5% rule. So KSP is going to be equal to X times 0.025 squared. So then when we square that value and we substitute in our KSP, this is what we're working with. We've got 6.25 times 10 to the negative 4th. We're going to divide both sides by that. X, which is equal to your solubility, is equal to 6.4 times 10 to the negative 8 molar. Okay, so that is your solubility of CaF2 in an NaF solution. And that's going to be significantly smaller than if we did this calculation without the common ion. So just out of interest, let's compare this answer really quick to what we would get if it was just being dissolved in pure water. So I've got those calculations ready for you. This is not in your notes, but just for interest. So we got our same ice table, except this time we don't have the common ion, so we get x and 2x. We plug that into your KSP, and you get x is x times 2x squared. And so that 4.0 times 10 to the negative 11 equals 4x cubed. And then when you solve for x, you get 2.2 times 10 to the negative 4th molar. And so that is quite a lot larger than we saw our answer before, right? Because this was to the negative 8th. And so, you know, that's off by a magnitude of 4. So that's really a very impactful change that we saw here with the common ion. So that's it. So what should you be able to do with this? You should be able to evaluate a system to determine if a common ion will impact the solubility of a salt. You should be able to use Le Chatelier's principle to discuss this impact qualitatively. So just talking about how adding a product will cause a shift back to the reactants, which will cause precipitation. And then you should be able to use KSP expressions like we saw in the sample problem to calculate this impact quantitatively. And that is it for Unit 7. Unit 8 will be all about acids and bases, and I'll see you then.